This episode is brought to you by Cisco Educational Premium. Did you know that spin is an inherent property of a quantum particle? Spin is a conserved quantity carried by elementary particles and thus by composite particles or hadrons and atomic nuclei. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. The orbital angular momentum operator is the quantum mechanical counterpart to the classical angular momentum of orbital revolution and appears when the periodic structure to its wave function as the angle varies. For photons, spin is the quantum mechanical counterpart of the polarization of light. For electrons, the spin has no classical counterpart. The existence of electron spin angular momentum is inferred from experiments such as the Stern-Galach experiment, in which silver atoms were observed to possess two possible discrete angular momenta despite having no orbital angular momentum. The existence of the electron spin can be inferred theoretically from the spin statistics theorem and from the Pauli exclusion principle, and vice versa. Given the particular spin of the electron, one may derive the Pauli exclusion principle. Spin is described mathematically as a vector for some particles such as photons, and as spinors and pi spinors for other particles such as electrons. Spinors and bispinors behave similarly to vectors. They have definite magnitudes and change under rotations. However, they use an unconventional direction, and I quote, "All elementary particles of a given kind have the same magnitude of spin angular momentum, though its direction may change. These are indicated by assigning the particle a spin quantum number. The SI unit of spin is the same as classical angular momentum. In practice, spin is given as a dimensionless spin quantum number by dividing the spin angular momentum by the reduced Planck's constant, which has the same dimensions as angular momentum, although this is not the full computation of this value. Very often, the quantum number is simply called spin. The fact that it is a quantum number is implicit. As the name suggests, spin was originally conceived as the rotation of a particle around some axis, while the question of whether elementary particles actually rotate is ambiguous, as they appear point-like. This picture is correct insofar as spin obeys the same mathematical laws as quantized angular momenta do. In particular, spin implies that the particle phase changes with angle. On the other hand, spin has some peculiar properties that distinguish it from orbital angular momenta. These properties are: 1. Spin quantum numbers may take half-integer values. 2. Although the direction of its spin can be changed, an elementary particle cannot be made to spin faster or slower. 3. The spin of a charged particle is associated with a magnetic dipole moment with a g factor different from 1. This could occur classically only if the internal charge of the particle were distributed differently from its mass. The conventional definition of spin quantum number is S is equivalent to n on 2, where n can be any non-negative integer. Hence, the allowed values of S are 0, half 1, 3 on 2, 2, etc. The value of S for an elementary particle depends only on type of particle and cannot be altered in any known way, in contrast to the spin direction. We will be seeing the spin angular momentum S of any physical system is quantized, the allowed values of S are S equivalent to reduced Planck's constant root S on n plus 1 is equivalent to Planck's constant on 2 pi root of n on 2 n plus 2 on 2 is equivalent to h on 4 pi root of n into n plus 2, where h is the Planck constant and h dash is the reduced Planck's constant, which is equivalent to h on 2 pi. In contrast, orbital angular momentum can only take on integer values of s, that is even numbered values of n. Those particles which have integer spins, such as have 3 on 2, 5 on 2, are known as fermions, while those particles with integer spins, such as 0, 1, 2, etc., are known as bosons. The two families of particles obey different rules and broadly have different roles in the world around us. A key distinction between the two families is that the fermions obey the Pauli exclusion principle. That is, they cannot be two identical fermions simultaneously having the same quantum numbers, meaning roughly having the same position, velocity, and spin direction. Fermions obey the rules of Fermi-Dirac statistics. In contrast, bosons obey the rules of Bose-Einstein statistics and have no such restriction, so they may bunch up together in identical states. Also, composite particles can have spins different from their component particles. For example, a helium photon in the ground state has spin 0 and behaves like a boson, even though the quarks and electrons which make it up are all fermions. This has some profound consequences. Number one is that quarks and leptons, including electrons and neutrinos, which make up what is classically known as matter, are all fermions with spin half. The common idea that matter takes up space actually comes from the Pauli exclusion principle acting on these particles to prevent the fermions from being in the same quantum state. Further compaction would require electrons to occupy the same energy states, and therefore a kind of pressure, sometimes known as degeneracy pressure of electrons, acts to resist the fermions being overly close. Elementary fermions with other spins 3 on 2, 5 on 2, etc. are not known to exist. 2. Elementary particles which are thought of as carrying forces are all bosons with spin 1. They include the photon, which carries the electromagnetic force, the gluon, which also the strong force, and the W and Z bosons, weak force. The ability of bosons to occupy the same quantum state is used in the laser, which aligns many photons having the same quantum number, the same direction and frequency. Superfluid liquid helium resulting from helium photons obeying bosons and superconductivity, where pairs of electrons, which individually are fermions, act as single composite bosons. Elementary bosons with other spins 0, 2, 3, and etc. were not historically known to exist, although they have received considerable theoretical treatment and are well established within their respective mainstream theories. In particular, theoreticians have proposed the graviton predicted to exist by some quantum gravity theories with spin 2, and the Higgs boson explaining electroweak symmetry breaking with spin 0. Since 2013, the Higgs boson with spin 0 has been considered proven to exist. It is the first scalar elementary particle, spin 0, known to exist in nature. And the last is that atomic nuclei have a nuclear spin, which may be either half integer or integer, so that the nuclei may be either fermions or bosons. The spin statistics theorem splits particles into two groups, bosons and fermions, where bosons obey Bose-Einstein statistics and fermions obey Fermi-Dirac statistics, and therefore the Pauli exclusion principle. Specifically, the theory states that the particles with an integer spin are bosons, while all other particles have integer spins and are fermions. As an example, electrons have integer spin and are fermions that obey the Pauli exclusion principle, while photons have integer spin and do not. The theorem relies on both quantum mechanics and the theory of special relativity. And this connection between spin and statistics has been called, and I quote, one of the most important applications of the special relativity theory. Since elementary particles are point-like, self-rotation is not well defined for them. However, spin implies that the phase of the particle depends on the angle as is theta for rotation of angle theta around the axis parallel to the spin s. This is equivalent to the quantum mechanical interpretation of momentum as phase dependence in the position, and of orbital angular momentum as phase dependence in the angular position. Photon spin is the quantum mechanical description of light polarization, where spin +1 and spin -1 represent two opposite directions of circular polarization. Thus, light over defined circular polarization consists of photons with the same spin either +1 or -1. Spin represents polarization for the factor bosons as well. For fermions, the picture is less clear. Angular velocity is equal by Rönnfels theorem, the derivative of the Hamiltonian, to its conjugate momentum, which is the total angular momentum operator J is equivalent to L plus S. Therefore, if the Hamiltonian H is dependent upon the spin S, the H on ds is non-zero, and the spin causes angular velocity and hence angular rotation. That is a change in the phase angle relation over time. However, whether this holds for free electron is ambiguous, since for an electron, S raised to 2 is constant, and therefore it is a matter of interpretation whether the Hamiltonian includes such a term. Nevertheless, spin appears in the Dirac equation, and thus the relativistic Hamiltonian of the electron, treated as a Dirac field, can be interpreted as including a dependence in the spin S. Under this interpretation, free electrons also self-rotate with the step-back effect understood as this rotation. Particles with spin can possess magnetic dipole moment just like a rotating electrically charged body in classical electrodynamics. These magnetic moments can be experimentally observed in several ways. For example, by the deflection of particles by homogeneous magnetic fields in a Stern-Gallac experiment, or by measuring the magnetic fields generated by the particles themselves. This episode is brought to you by Cisco Educational Premium.
After 40 days, Fior is unable to solve Totalia's questions, not even a single one. We should not come as a surprise since Fior wasn't that talented mathematician and was just hiding behind his teacher's work, Scipione del Ferro. And so Totalia becomes the math kingpin of the town and Fior has to abide. What a math jewel. We should have one of these fine days, but maybe no. So, coming to think of it, Del Ferro was the only man in the world who could solve depressed cubics. So how did Niccolo Totalia manage to solve the hardest problem known? How did he solve the depressed cubic equations? As the saying goes, necessity is the mother of invention, because solving the depressed cubic equation was necessary for his career. Totalia had to become creative. He extends the idea of completing square into completing the cube. For example, he takes the cubic equation x cubed plus 9x is equivalent to 26. Drawing the analogy from before, we can think of x cubic as a cube with sides of length x. The 9x term is a cuboid of volume 9x, and the whole thing adds to 26. So as before, we need to do a similar thing and complete the cube. Imagine extending 3 sides of our cube, a distance y. This will obviously create a larger cube with side z, z being equivalent to x plus y. So we have the original cube deep at the corner, and we can break the new bigger cube into 7 shapes. There are 3 cuboids with side x by y, and narrower cuboids with side x by y, and then finally a cube with volume y cubed. Totalia then rearranges the 6 cuboids into 1 cuboid with length 3y, with z and height x. This cuboid represents the 9x in our cubic equation. So putting the big cube back together, we find that we are missing the small y cubed. So we can complete the cube by adding y cubed both sides of the equation. X cubed plus 9x plus y cubed is equivalent to 26 plus y cubed. X cubed plus 9x plus y cubed being z cubed 3yz is equivalent to 9. Now we have z cubed, the complete larger cube equivalent to 26 plus y cubed. Now we have 2 equations and 2 unknowns. The first equation is 3yz is equivalent to 9, and the second is z cubed is equivalent to 26 plus y cubed. By solving the first equation for z and substituting the second, we get z is equivalent to 3 on y. 3 on y cubed is equivalent to 26 plus y cubed. Then y cubed plus 26 is equivalent to 27 on y cubed, which is y raised to the 6th plus 26 y cubed is equivalent to 27. Y cubed being its own variable, we get y cubed square plus 26 y cubed is equivalent to 27, which is a quadratic equation, and we know how to solve it. Even Fiore or Pacioli knew how to solve it. And so from this we get y is equivalent to 1, z is equivalent to 3, x is equivalent to 2. This is the solution to the cubic equation. And so this is how Niccolò Totalia became the second smartest mathematician in the world. He summarizes this as a poem. Remember, algebraic notation has not been invented yet. Totalia's victory in the duel makes him a celebrity, much like Rihanna or Quavo, but in math. Mathematical community is eager to hear from him. Everyone wants his attention. Girolamo Cagano, our 5th character in the story, is a mathematician based on Milan. He too wants to hear from Niccolò Totalia, but as with celebrities, it's not easy to interact with one, and as they are usually adamant to hear anything from their fans, and no one is more adamant as Totalia, as he is to the mathematicians around the world, especially Girolamo Cagano. He refuses to reveal even a single question from the competition. However, Cagano is persistent, and he manages to box Totalia. On March 25th, the same year, 1539, Cagano manages to lure Totalia to Milan, and Totalia tells Cagano about this method of solving the pressed cubic equation. But there was a catch. Aside from introducing Totalia to his wealthy benefactor, Cagano has to swear solemnly that he would not tell anyone the method. He wouldn't publish it in any way, and will only write it in cipher. And as Totalia quotes, so that After my death, no one shall be able to understand it. Girolamo Cagano begins playing with Totalia's method. Now that he has a way to solve the depressed cubic equation, he wants to find a solution to the full cubic equations, including x squared term, and he finds it. The problem is he can't publish it because of the solemn oath he gave to Totalia. And why does he want to publish it just like that? You see, Cagano is a doctor and doesn't need a math job to make ends meet. And for him, the credit is more important than the secret. But then, what gives? In 1542, Girolamo Cagano travels to Bologna, where he visits a mathematician who happens to be the son-in-law to Scipione del Ferro. Remember him? Our second character in our story? Cagano finds the solution in Del Ferro's old notebook that was shared with him during the visit, and it predated Totalia by decades. So now he can publish his work without violating the solemn promise he gave to Totalia. In 1545, Cagano publishes Ars Magna, the Great Art, an updated compendium of mathematics. In it, he acknowledges contributions of Del Ferro, Fior, and Totalia. However, Totalia is not happy with this. But maybe to keep this in mind, these guys are still using the geometric analogy to solve these equations. The problem came when Cagano encountered problems that involved the negatives. He asked Totalia about this, but he could not solve it too. After all, how could you complete a square by adding a negative area, or complete a cube by adding a negative volume? So what does Cagano do? He ignores the possibility, affirming that the square roots of negatives is as subtle as it is useless. Around 10 years later, our last character in our story, the Italian Raffaele Bombelli, solved these problems that involved the negatives. How did he do it? He stubbornly went through with the calculations using Cagano's method, disregarding the geometrical paradoxes that the square roots of negatives implied. He finds out that the square roots of negatives cannot be called positive or negative, and he lets it be its own type of number. It turns out that Cagano's method works if you stop paying too little and just abandon the geometrical analogy for a moment. This new number was later termed as imaginary number by René Descartes, and later Leonhard Euler introduces the imaginary number I being equivalent to root of -1, whose coordinates lies perpendicular to the real number line. Personally, I think it is the worst name ever. Imaginary, isn't it as real as any other number? This imaginary number, when coupled with a real number, gives us the complex number. Today, complex numbers forms the cornerstone of the mathematics that shape our world. From Euler's formula, e to the ix is equivalent to cos x plus I sin x, to Schrödinger's equation.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.
Yeah.